Alright, so remember what our goal is now. We're given this original data, and we want to try to predict the future. I'd like to predict if I put in position 16, it'll give me the frequency, and the prediction is something I can rely on. Alright, what we've been studying is, let's try to fit a line to this data. Okay, the first thing we do is we take a look. What do you guys think, just visually? It's darn good. There's a couple things I want you to talk to me about. Do we have a positive or negative association? Absolutely a positive association, and it looks pretty darn linear. This is great. Okay, so let's draw that graph. And let's go to work. Now remember, the eyes can be deceiving sometimes. So let's go ahead and assess the fit of this graph. So the next thing I want to take a look at is we want to take a look at correlation. So let's do that. We create the equation for that line. Equations are in L1 and L2. This is the actual equation of the line that best fits this data. It has a y-intercept of 381.77 and a slope is 36.44. I didn't ask you to interpret those things, but you're going to have to tomorrow for each position. Okay, the hertz goes up 36.44.
Repeat how you got to that screen.
Okay, so I went stats, calculate, and down to 8. Alright, but what I'm focused on now are these guys. And I find that correlation is 0.995. Wow. Okay, what are my 4 fancy words for this guy? Strong. I might even throw a 5th one in. Very strong. Positive linear association. Things are looking good. R squared. Now I was looking around at your R squared. Some of you I'm not happy with. Okay, I need all the right words here. 9.1 is probably better. I need all the right words here. Now remember what R squared is referring to. It's called the coefficient of determination. And what it means is, if I would have just guessed the mean every time, the mean of these numbers, I'd have had a lot of errors. But you know what? When I fit that line to those points, 99.1% of the squared errors, we've got to square them, but 99.1% of those errors go away. The line explained away all of those errors. So your big fancy sentence, 99.1% of the variation. Some of you say, squared errors there. That's fine. 99.1% of the variation is explained by the least squared regression line predicting frequency given position. Okay, I saw a lot of people out there just giving me the 99.1% of the line is explained, or of the variation is explained by the line. It's not good enough. Okay. Give me the entire explanation. So this is incredible. Alright, let's go figure out the standard error. Now on your paper right now should be your formula. SS resid over n minus 2. Now, I'm asking you to ask, what's the difference between SS resid and SSE? It's the same thing. We're going to go find all the residuals. We're going to square them and add them up. So how do we do that? Okay. Remember, a residual is the vertical distance, the distance in the response variable from what actually happened to what is predicted to happen. Now, a little hint for tomorrow maybe. You are definitely going to have to use the residual formula on various parts of the test. It's not going to be good enough just to throw them all in L3 and get it done. So you have to know that formula. Question. If I gave you the residual, and I gave you the predicted, could you solve for the actual? Bet. That's a little hint. I'm not telling anybody else. The other classes will tell you guys. Okay? So be aware. That might come up tomorrow. Okay, so how do I do those residuals? The actuals are in L2. Deal with it! Here we go. L2 minus, don't forget your parentheses. You've got to distribute that minus. A lot of you have just backwards residuals because you forget to do that. All right, face the equation. Plug in L1 right there. Blammo. And there are my residuals. Now what's standard error all about? Well, how big are my errors? How much are my predictions missing the actual values here? All right, now we can't just take the average of these because technically what is the average residual going to be? 0. Yeah, they add up to 0. So we got to square them and add them up. That's SS resid. All right, so I'll do a 1-bar stat on L3. This is the guy that squares and adds them up. So on your paper right now, it would be the square root of 2,208.1 divided by 11. And I think that comes out to about 14.1.
Yep.
All right, now I hope you don't have on your paper the standard error is. What does it mean? When using our least squared regression line to predict frequency, typically our projection model is off by about 14.1 hertz. That's what standard error means. Now, is it a big number? This is kind of a next level kind of thing, but is that a big error? Well, let's take a look at these. This is what they come in. Is being off by 14 that big of an error? No, I don't think so. Not bad. Now, if these numbers were like 9, 10, 11, 12, being off by 14 would be a big deal. Okay, but I don't think that's a terrible error, so everything's looking good. All right, last step, let's graph those residuals. See what happens. So we'll do a scatter plot on L1, L3. Zoom stat on it. And now we have a problem. This, remember, is what we're on the lookout for. This residual plot tells us a couple of things, but the one thing it tells us is the line is not as good a model as we want. And remember why this is a bad residual plot. Take a look at these errors. They're going to keep getting bigger. Now remember I told you I wanted to plug in 16? So this was the position 1 through 13. So if I'm plugging in 14, 15, 16, you're going to get a huge error. So no, this blows everything up. Everything was going incredible. But that tells us that no, you're going to get huge errors. So that residual plot, because of that pattern of increasing errors, a line is not the best fitting. So all that's for tomorrow. That's tomorrow stuff. Okay, so that you got to be able to do backwards and forwards.
How would you label the residual graph?
Yeah, well this is the residual graph. I did L1 against the residuals. So the L1's, this axis was the position. And I'm sure it goes from like 0 to 13. And then these were the residuals. These were the errors. Another question? Yeah.
I get everything. I just don't understand how something can be so good and then be so bad.
Yeah. Well, let's go back to the original graph. Let's go look at this thing again. Now let's take a real cynical look at this graph. We were all excited when we saw it at first, thinking everything was great. Now let's take a really good look at that thing. Do you see that curve? It's there, isn't it? It's hard to see. Remember, the naked eye is not so great. You can make mistakes, but there's a curve there. So a line's not a bad predictor model, but there may be a better one out there we can fit a curve to that would actually be a better prediction model. Now, in statistics, there's all kinds of different models you can come up with. I mean, if this was a bunch of points in a circle, we could go find the equation of that circle to predict the future. Okay, there's quadratic models, all kinds of models. But for this course, first year of statistics course, there's two types of models that we're going to know backwards and forwards. And one of them's the exponential model, which we're going to talk about today, and the other one's the power model, which we'll talk about next week. You have to know the theory behind it. And how in the world do you fit a curve to those points? Okay, and that's what we're going to work on today. All right, so today we're going to work on this thing called the exponential model. We've been working on linear growth. What does linear growth mean? Let's say I have an equation of a line. Y is equal to 2x plus 3. I plug in points, right? I plug in a 0, I get a 3. I plug in a 1, I get a 5. I plug a 2, I get a 7. I plug a 3, I get a 9. Whenever you have a linear model, what it really means is that your response variable is going to keep going up by the same constant. It turns out to be the slope, right? It's going by 1. It'll keep going up by the same constant every time. That's the linear model. Well, what's the exponential model? The exponential model is that you keep multiplying this by something. That same something every time. For example, I'm sure some of you have heard this before. Let's play a game. Take one or the other, okay? I'm going to give you a penny today. Tomorrow I'll give you 2 pennies. Third day I'll give you 4 pennies. I think I got that right. Next day I'll give you 8 pennies. Next day I'll give you 16 pennies. So 4 days into the month I'm giving you 16 cents. That's the exponential model, right? I keep multiplying by 2, right? So we'll do that for a month. I'll give you that much money, or I'll give you all the money I make the rest of my life, my whole life. Which one of those would you take?
Penny.
And it's the penny one. You'd think, well, wait a minute. So the 5th day, you're giving me like 32 cents. And the 6th day, the month's almost half over, then you're only giving me cents. Do 2 to the 31st power in your calculator real quick. That's 2 times 2 times 2 times 2 times 2. Check out that number. Go over a couple decimal places for the pennies, and that's what you would be owed. So my point is that exponential can grow pretty fast. Now you might have an exponential where you keep multiplying by 2. You might have an exponential where you're only multiplying by half, and it's going down all the time. That's exponential decay. Okay, but exponential means you multiply by the same thing every time. So one of the first things, and this is what you do on your homework tonight on one of them, if you think that maybe, just maybe, this data that you have might be exponential, and you want to just do like a quick dirty test to see if that's possible or not, we want to see if we keep multiplying by the same thing to get the next number. One way you can test that is you can do division. So if I do 880, this is the homework problems, make sure you get this down, divided by 830.61. So let me throw that in your calculator real quick. Tell me what that comes out to.
1.06.
1.06 about. All right, so if I multiply this by 1.06, I get this guy. Now do the division for the next 2. 830.61 divided by 783.99. 1.06. Do the next one. 783.99 divided by 739.99. What do you get? They're all about that same multiplication factor. No, not linear. This is exponential. That means if I take that guy and I multiply it by 1.06, I get that guy. And I multiply that guy by 1.06. If you multiply by the same thing every time, that's exponential. Okay, so now I'm thinking, you know what? An exponential model might be a better model to predict for that. So if I'm thinking that exponential might work, all right, here is the process that we go through to find out what that equation is. This is exactly what you're going to do on your homework this weekend. Okay, what you see on the board and how I'm doing is how you're going to break up your homework tonight. But here are the steps, and here's what we're going to do. We already did number 1. We took our original data. We went through all of the analysis. Now, you have sentences here, of course, little short sentences. But ultimately, we decided, you know what? A straight line is not the best fit. So here's what we're going to try to do. We're going to try to take this original data and make a straight line out of it. Right now, it's going kind of like this, isn't it? We're going to try to do something, transform this data, so that, so here's the, so the x-axis, I'll just call it x and y right now. We know that's position and that's frequency. But I'm going to do something to the L1s or L2s. I'm going to do something that will linearize this graph. So when I'm looking at this, and don't peek ahead on me here, but when I'm looking at this, what's preventing this from being a straight line? And as I look at it, the straight line would be kind of going like this, but the y's are going too fast, aren't they? They should be kind of calming down a little bit. If the y's would just calm down a little bit, not go so fast, then this thing might have been a straight line. So what is one thing that you think we could do to that response variable, to those y's, that would calm it down? What's that?
You can alter the slope.
It's not a straight line. Remember, we're talking about what would you do to the response for those numbers in the y's that would make them go slower? Divide. That's great. So let's cut them in half. Let's divide them all by 2. Well, let's see what happens. Okay, so that'll calm them down for sure. But notice what happens here. You guys don't have to do this. I'm just going to show you. So there's my original graph. Got a little bit of that slant to it, right? I'm going to go in And I'll get rid of these residuals now. I'll take all the L2s and I'll cut them in half. I'll divide by 2. Did they calm down? Are they smaller? You bet. Now let's take a look at the graph. It's going to be the same, isn't it? We did cut them down, but they're all cut down in the same ratio. So we still got that. All right, we got another idea. What's something else we could do maybe to calm them down?
Square root.
Square root's a great one. And take a look at this. I wasn't expecting this, but I'll show you that we did the third period. I was like, oh my gosh, this is great. Square root of the L2s. And now let's take a look at this. Now let's take a look at this graph. Looks pretty good, doesn't it? Well, how could we tell how good of a job we did? What would we do? Go through all the process again. Now, like I said, there's all kinds of different mathematical models. This is one of them. Square root the response variable. That's the quadratic model. But that's not one that we focus on in this particular class. But this looks like it might be good. The better job you do at linearizing the data, the better curve you're going to have at the end. You'll see how that works. All right. Well, what we do to calm down the y's in an exponential model is take the logarithms of them. Logarithms. You thought you were done with them, didn't you? I hate logarithms. I don't understand logarithms. Literally, I think last year I figured out logarithms. Just a little bit. I've been teaching this for 15 years. So I'm with you. If this is hard, just kind of stay with it. But here's what I figured out. Logarithms, they're just the exponent finders. That's all they are. I mean, why did you call it log if it's just you're finding the exponent? Let me show you what I mean. You guys are okay with this, right? 5 squared is 25. That's true, right? Yeah. Well, here's what logs do. So you have the base here, the answer here, but what it spits out is the power. It's just the power finder. Come on now. I was like a math major in college. I didn't know that. You guys, nobody's with me on this? That's just like, that's all it is. Why do you call it log? Call it power finder. All right, now I need you guys to kind of remember some of these things from like the crazy identities that you guys had to learn. Now, how about this? This should be okay, right? How can I instead of writing in a logarithm form, how can I write it in standard form? In other words, get rid of the log. This is one thing you're going to have to know for today. Well, remember, and this is what I taught it like in Algebra 2, you circle the base, and that's the power, and that's the answer. You okay with that? That's the base, right? So that power makes this. Keep that in the back of your head. How about this guy? This guy okay? 10 to the 2 plus 3, that's 10 to the 5th, right? Isn't that 10 to the 5th as well? 10 times 10, 10 times 10 times 10. I'm not getting any nods out of you. You guys are with me on logarithms, aren't you? This is okay, right? This is true. All right, this is the one I don't know. I still don't understand. So, if you have a log to a base, and then that's the same base, the power you get here is the answer. Isn't it a power finder? So the power you have, if you have the same base, somebody last period said, hey, wait a minute, can't you just bring that out front? And then the log base, the same base is always 1. I don't care how you remember it. Okay, that's just something to keep in mind. These are the two we're going to use today, and then Monday we're going to be using that thing. So just if you know these two for today, you're okay. Okay, so let's do this. Now, don't freak out as well. When I just tell you logarithm, log, what is the base that's assumed? 10. It's log base 10, right? In these problems that we're doing, we also do the natural log. What was the base for the natural log? It's E. Remember E, 2.7, something like that. So don't worry, you'll see it done both ways. It's no big deal. The math will come straight out at the end. It's just to understand you can use either one of those logarithms in your fund. All right, let's go through the progress. So now we're going to take a look at the transform data. So what I'm going to draw a graph of now I'm going to go into L3 now, and I'm going to take the numbers I have in my response variable, I'm going to take the logarithm of them. Log of the L2s, and this is what I get here. Calmed them down a lot, didn't it? Now remember what that is, right? That means 10 to that power is that. 10 to that power is that. That's what the logarithms are. It's just telling you what powers, in this case to the base 10, that give you that final number. All right, let's graph these two now. Let's graph our transform data. So I'm going to do a graph of L1, L3. That's already set up. Nope. There's my graph. Now, what am I doing here now? So now my axis, this is still, down here is still the position, X. And now over here is actually the log of Y. The log of the frequency. So this goes from like 0 to 3 or 2 to 3 or whatever they set that up at. But take a look at our graph now. All right, so how well did we do? Remember, the better job we do at linearizing this data, then the more accurate my ultimate model is going to be. So what do I got to do to see how well it did? Let's go assess the line again. So let's do the whole process again. So let's fit a line to it. We'll go down to 8 again. Now, remember, my data now is in L1, L3. That's where my data is now, my transform data. Blammo. Wow. Now my correlation is 0.9s as far as the eye can see. Stronger, yet positive linear association. By R squared, again, 99.999% as far as the eye can see. So how did I do? Did I linearize this data even more than before? And that's what you want to focus on. The better job you did right here is going to tell us ultimately how good of a fit our curve is going to be. That's where I want your focus to be. We're going to go find standard error. We're going to do the residual plot too. But that's really what's going to tell us how good of a transformation we did. All right, let's go do standard error. So let's go find the residuals. This is all good stuff for tomorrow. So I'll put those in L4. So the residuals now would be L3 minus parentheses, paste that equation. All the same stuff we've been doing. That's still L1. Look at the residuals there. Remember what that minus 6 means, right? That's 0.00000. Now we expect the numbers to be smaller because we did take a logarithm that made the numbers smaller. Okay, but those are pretty minute even still. Okay, so if I did a 1-bar stat on the L4 and I was going to go do the standard error, it'd be the square root of 0.0, 10 zeros, and a 5. We're getting pretty small errors here, aren't we? And then divide by 11. I'm not going to figure that up. I'll just write tiny. That's really tiny. All right, let's go take a look at our residual plot. And like I said, come back and watch the video if some of this stuff is flying past you. All right, let's take a look at the residual plot here. Man, that's a beauty. Look at that thing. That's a nice random scatter. That's what I'm talking about. So my assessment of how well a straight line fit my transform data is stellar. Yeah.
Since you're still using a line to assess the fit, are the residuals proportionate?
No. You would not want to compare these residuals, this standard error, against that standard error. I don't know if that was your question, but remember these came from logarithms, which were smaller to start with.
Yeah, that's what I meant. They like proportion it to the new data set.
Yes, these standard errors and these would be proportional to this data set, my new data set, L1, L3.
Oh, okay.
Yeah.
Okay, so when you did your residual plot, did you use, because L1 is position.
Yeah, this is still position, so you're going to be going 1 to 13 here. And then these were those tiny numbers, like 0.00000. You look in your window and see how small those were.
How did you get those, the y-axis, or the...
Go into your window. I mean, how do I know what numbers those were?
Well, yeah, because I have my... I had L3, L4.
What did you do L3, L4 for? This is L1, L4. This is still the original data.
Right.
And then I put the residuals over in, because my logarithms were in L3, so I put the residuals in L4.
Are we normally going to be looking for data that's accurate, or
No, it's not hardly ever going to be this accurate. Really what you want, how well did we fit here? How well did we do it? Did we do a lot better than we had before? If we did, then our curve is going to be better than our line was. And sometimes, I'll show you this, the example in the book, hey, this is great, this is tiny, but this has a little bit of a curve to it. That doesn't concern me as much here. Now, it might mean there's still a better model out there, but here's where I want my focus to be, on how well it fit the line. Yeah?
So this is what we would have on the work.
Yeah, tonight you're going to be doing this.
We have 2 graphs.
Yeah, you're going to have more too. Yeah.
So if we're that small, would you put tiny or would you actually do
Well, go figure it out. Somebody's here.
that? Would you actually do that?
Yes, you actually do that. All right, now. All right, let's go back now. What was the equation that we actually fit to this transform data? And I'll just write it as y hat. So if I go back, I don't have it in my calculator right now. So stat, calculate, this is from L1, L3. So the equation that fit this transform data was 2.618 plus 0.025 x. Now, what I want to do is actually go find the equation that doesn't fit this transform data. I want to find the equation that fits the real data, the original data. So now we can go back to the original. Okay, so I'll show you that graph again. And on tonight's homework, you're going to have 3 columns like this, and you're going to go through all these steps. So back to the original graph, L1, L2. Our original graph. So what is the equation that fits the original graph? And it's this. What we're going to do is we're going to rewrite this equation, okay, but from the logarithm's point of view. So the log, log base 10 of y is equal to 2.618 plus 0.025x. Now notice I'm not writing in what these variables represent because we're going to do some math work here. This is an exponential equation. This is the equation of a curve. How did I get it? I just wrote the equation I got off of this. This was really the log of the y's. To fit these points, that's the equation that fits the points, but I took the logarithm of the y, so I'm writing it like that now. And this is an exponential equation. Okay? All right, let's write it without logarithms in it. So let's do this. Okay, so let's rewrite that equation without logarithms. Remember, you circle the base. That's going to be your power. Okay, so that's that thing right over here. So what have I got? I've got y is equal to 10 to the 2.618 plus 0.025x. These equations are exactly the same thing. They're just written a different way. This is the guy I want you to put in your calculator. Because when we cut and paste it, we'll keep all the significant digits in there. Let me show you how to do that. This equation is what I want to put in the calculator. Okay, so let's go to our y equals. So we're going to do 10 to the second log. And now let's just paste this equation. This is the equation that's in our memory. So vars, statistics, equation, and then close off your parenthesis. Now why this is so good is it keeps all these digits, and whenever you raise something to a power, these digits are a big deal. Right now, draw your graph. Go back to your original graph. Plot L1, L2, there it is. Do a zoom stat on L1, L2, and let's see how good our curve does.
I just kept, well, I didn't write it all the way out and paste it, and I just put 10 times 2.618, because I didn't continue it, but I did.
No idea where you said.
Okay.
Okay, this equation is now in our equation editor. Okay, and notice now it curved and it hit the point. Now, how did I know it was going to be that good? Right here. Right here. Because when I did the transformation, I really linearized that data. So that when I go back to where I started from, okay, it's gonna fit real well. And obviously we see it fits those points very well. Okay? And even right now, so if I wanted to plug in 16, let's say, and rewrite the equation, you put a 16 in there, but now if you go to your table and plug in 16, that's going to give you a prediction with all those significant digits. So the prediction for 16 is 1,046.5. Okay, all right. But that's not the equation in really exponential form. This is the basic standard form for an exponential. A and B. A is the initial position, and B is that multiplication factor. What do we keep multiplying by every single time? So we got a little bit more work to do on this to get it into the correct form. All right, what we're going to use now is this guy. Remember I said if you have two things added together, you can write it with two base 10s. It means the same thing. Let's go do that over here. So this is going to be y is equal to 10 to the 2.618 times 10 to the 0.025. Is everybody okay with that? Just using that identity. This is A. Put that in your calculator. 10 to the 2.618. That represents the A in our equation. $400 something? 414.95. This represents our multiplication factor. We'll put that into your calculator. 10 to the 0.025. It should be around our 1.06, I'm thinking. Okay, so this is 1.06, and the x stays up there, and there's our equation in standard exponential form. Couple of things now. This equation is the same as this one, just written a different way. This equation is the same as this one, just written a different way. This equation is the same as this one, just written a different way. All of these are the exponential equation that fit those curved points. All right, just threw a ton at you here. Let's start from the beginning. I have an original set of points. I'm going to try to fit a line to it. This data that we looked at, everything was great until we got the residual plot. That residual plot tells me, hey, something might be up. You want to test out exponential quick and dirty? Go do some divisions and see if you get the same multiplication factor. If you do, and you have to do that on one of your problems tonight. If you think it might be exponential, The transformation that will get us to the exponential equation deals with logarithms. Why is it going too fast? Let's calm them down. Let's take the logarithm up. Turns out when we took the logarithm of the initial data, it was unbelievable how much we linearized the data. This tells us that we have found the right model. Okay. So this is the equation of the line that fit the transformed data. Writing it this way, using the logarithm, is the equation of the exponential. And this is the guy we just put on our calculator so we can keep all our significant digits. This is the work that needs to be done to get it to the right form. Yeah?
Would we also write it out in the sentence form? Frequency?
Yeah, so now's a good time to go ahead and put frequency in hertz is equal to, and then up here would be position. Absolutely. Okay?